Greetings to one and all present here. I welcome you all to the CIT Quantum Hackathon 2022 workshop series sponsored by IBM Quantum as part of Qiskit Fall Fest. I would like to quote a famous saying by Carol Burnett: when you have a dream, you have got to grab it and never let it go. With this, I'm extremely pleased to welcome our guest speaker, Mr. Vishnu Ajith. He is a Qiskit advocate who entered quantum computing due to his curiosity about the physics of computation. He holds a professional certificate in quantum computing and quantum internet from Delft University. He completed his undergraduate from IIT Kottayam and has made contributions to a number of quantum open source projects like Qiskit Textbook, Penny Lane, and Qrand. He is currently working as a graphics hardware engineer at Intel. His research interests include quantum machine learning and quantum cryptanalysis. With all these introductions, I am pleased to welcome you, sir. The session is all yours.
Thank you. Thank you very much. So we'll get right into it. At any point, I've been told that, at times I speak rather fast when I get into things. So at any point you feel like I'm not clear or you want any clarification, feel free to stop me and ask. I can't quite see the screen, so if any questions come up, like in the chat box, I will not be able to see. I'd request one of the co-hosts to just let me know if a question comes up in the chat at any point.
Okay, sir. Sure.
Yeah, thank you. So yeah, so I'm here to talk about variational quantum algorithms and why they're important. What are some to sort of give you a basic idea about variational quantum algorithms and to set a sort of foundation of things. And as with any quantum computing talk, throughout the talk, you might feel like you're missing out on many parts, and you might feel like you're not understanding some things. But my only sort of request is to stick on, because it's sort of more important that you keep listening and then you are at least familiarized with the words. Most of the learning in almost any subject comes when you sit down and decide to self-study. The sort of main motivating point behind talks like this is that you're familiar with the words. So when you come across something and when you decide to sit down and study this by yourself, and you read the literature or you read some of the resources I'll point out or anything like that, you'll be very familiar with the words. You'll have at least heard of them. It won't seem so intimidating to you at that point. And that is sort of the main motivation behind webinars and things like that. So again, even if you feel a bit overwhelmed in between, because there's a lot of stuff coming in from different areas, just like keep an open mind, just listen through the whole thing anyway. All right, to start off, we'll just very quickly look at quantum computing again at a glance. I'm sure there's been a lot of webinars which have gone into this in detail. But just to make sure that we are all on the same page and we are all thinking along the same lines, we'll just go through the whole thing very quickly once more. So quantum computing is using quantum effects like superposition, entanglement, and interference in computing. And this means so it's very important to realize that this is not like an extension of classical computing. It's not like like GPU, APU, and the next thing. This is a completely so even though quantum computers are very often marketed as QPUs and another processor, it's very important to know that this is a completely different paradigm of computing, as in the way you think about computations and everything completely changes over here. It's not like how you think about it. So whether you run a code on a CPU or a GPU, it's essentially the same idea, just that you're running it on a sort of different architecture. However, when you think of quantum computing and quantum programs or quantum circuits, the entire idea is completely different. We are thinking about it from a completely different paradigm. For example, when you write any, let's say you're writing code and you decide to write any program, what you're writing code on is about a lot of layers of abstraction. So at the end of the day, what your computer chip actually has is a lot of transistors. And transistors that work in different ways, that do AND gates, NOT gate, and that's the first layer of abstraction. So when you connect transistors in a certain way, they act like an AND gate. Another way, they act like a NAND gate, OR gate, multiplexers, which are sort of built together from different AND or NAND gates. And then one layer above, you start looking at it like a control unit, an execution unit, parts of the CPU. And then the layer above it is when you start writing in assembly language, when you start coding in assembly language, you sort of assume that there is a machine which knows how to do this. You don't really have to know how the machine does it. It's not really your problem. But there is a machine which can do these things, these instructions, and that happens. And then there is OS, which is one layer above the assembly language as well. So the OS, so anyone interfacing with OS does not have to know what the underlying hardware is, or what sort of transistors are being used to run whatever program you do or anything like that. As long as they are considered, there's a set of system calls which you can make. And as long as you make those calls, the computer will do whatever you want it to do. And then when you start programming, say in Python, C++, Java, there's yet another layer of abstraction on top of it. So you're talking essentially to the OS and to some parts of the CPU, and you know what the language's specifications are and what the language can do. You're not at all bothered about what transistors or what logic gates are being run in the background. How is the memory kept? You could be for like higher levels of efficiency, but you generally do not have to know any of that.
Excuse me, sorry to interrupt, Vishnu.
Yeah, please.
Are you sharing a screen now?
I mean, I was sharing just I haven't really shown anything. So yeah, I'll just forgot that.
Yeah, it's okay.
Thanks for letting me know.
Yeah.
Right,
Yes, it is visible now.
Okay. So I'm still in this.
Yeah.
So this is the sort of first line I read out. And so there are so many layers of abstraction on top of that, you never really know what's happening underneath it. But in quantum computing, we are at a very, very, very nascent, like very start of stage things. We're still making circuits here. Okay, so everything we'll be doing in terms of programming is we'll be writing circuits. We'll be writing a CNOT gate or a X gate or NETS gate. Or if you decide to look at like other forms of quantum computing, like optical quantum computing, something, you'll be writing beam splitter gates, or you'll be writing Gaussian gates and things like that. But pretty much everyone is still at the level. So you're like one step even behind assembly. Okay, maybe at assembly level, we have quantum assembly languages. But it's very important to know that that is the layer of abstraction that we're working with. And fundamentally also, quantum algorithms work in a completely different way from normal computer algorithm you would see. So that's sort of a fair warning situation there. And then, but we still have some analogs. So some things which correspond, like some things in the classical computer which look very similar in a quantum computer. So for a bit, you have a qubit. So that's the quantum analog of a classical bit. But that's about where the similarity ends. If you take any random bit in a computer, it'll either store a low voltage or a high voltage, which we interpret as 0 or 1. And the whole idea of computation is the electrical currents are manipulated in such a way that whatever result you want is produced. But in a quantum computer, the whole quantum thing comes in that this equation plays in. The very sort of last equation plays in. It's not that your bit is either 0 or just 1 anymore. So you can have what's called a superposition of states for your bit. So in a classical computer, a particular bit will have the state either 0 or 1. But in a quantum bit can have sort of superposition of states, or it could be any state. So this alpha and beta are completely random variables. So any complex variable, as long as they can be normalized to 1. So alpha square plus beta square should be equal to 1. As long as that goes, any complex variable fits in here. And so it's obviously difficult to imagine a complex number of 0 plus complex number of 1 being stored in a bit. And that is true. So even though we say superposition, very often it's quoted, sort of misquoted in popular science, that a superposition is an AND of 0 and 1 or an OR of 0 and 1. It's very important to note that there is no classical analog for a superposition. So there is nothing in our classical world, the world we live around, which actually does superposition. So it's important to understand that this is not 0 and 1. This is not 0 or 1 or anything like that. The word is superposition. It's a new word that we put in because we didn't have anything till now. And superposition. And just like that, this goes very much against our common sense of things, right? A lot of things in quantum mechanics, like superposition, entanglement, all look very. They all look very weird to our normal sense. Like when we throw a ball at a wall, we expect it to come back. We don't expect it to pass through the wall. So it makes sense that a common sense very often doesn't work there. And so what we fall back into is very rigid strong mathematical proofs and arguments. And these notations, which I'll also look into a bit in the next few slides, are some examples of that sort of mathematical notations. Right. So this first one, you'll come across this notation a fair while. This is a ket notation. And generally what a ket notation stands for is a column vector. So any column vector of complex numbers, x1, x2, x3 here are all complex numbers. And as long as you write any column vector filled with complex numbers, that's you can like give it a new variable name called x and ket x. That just refers to this. This is a fairly physics notation. And then when you decide to take the complex conjugate, so you just flip horizontal to vertical and vertical to horizontal, and then you flip the sign for the complex bit. So the a plus ib becomes a minus ib. So you take the complex conjugate of things. You get what's called the bra notation. So the bra and ket, they're just notations which physicists have used for a long while because it makes easier to write some of the math which is needed for quantum mechanics and quantum computing. Nothing to be very intimidated of, just new notation. Just think of it as a new sort of symbol which comes in. And what the symbol stands for is, unlike in a classical bit where if you say 0, it's 0 and that's done, it's sort of more complicated to write down how quantum bits work. And this should have been a square bracket for vectors. But a 0 stands generally for the lower state, and 1 stands for the higher state. And a good way to represent this in terms of vectors is 1, 0 and 0, 1. And again, this might not make a lot of sense at this moment, but over time, when we build up to things, it'll start making a lot more sense. And I said earlier that this is the general form of any qubit. Any qubit, any single qubit can be represented in this sort of particular form, unless it's entangled. But let's not look at that right now. We'll get into it step by step. And sort of when you start, so instead of the 0, ket 0, when you substitute it with this, and then when you substitute ket 1 with this, what you get is you sort of multiply this in here and you multiply this in here, and you'll see that you can represent this same thing as a column vector now. So alpha and beta. What I did is I've just substituted these into the earlier equation and I've just put it together. And so, yeah, so like I said earlier, I mentioned a while ago that, alpha square plus beta square has to be 1. And the sort of reason for that is that, so say you have a random qubit which is in this state, and then you measure it, say, 1,000 times or 100 times. So this will be the probability. Sort of alpha square will be the probability that the value get is 0, and beta square will be the probability that the value get is 1. Again, all of this seems very contrived and, like doesn't really seem to make a lot of sense at the level you're thinking, but that's exactly why we have this notation. It is very contrived, and good lot of the reason in quantum mechanics for anything being what it is that it works. So it works, and all the calculations we do still work. So we have sort of decided to stick on to it. We still don't know, and we know that we cannot know some things, and we sort of make peace with it, and we live on with what we can do. So that's the sort of reason why we have all this very weird looking notation, symbols, weird ways of writing down 0 and 1, ket, bracket notation, all of that. And so we have gone over ket and bra notation. And then, so this is the bracket, which is essentially when you substitute these two back in here, you instead of, like writing 2 lines, you could just put them all together here. So you'd be doing is, so this would be the value you come into, x1 conjugate is x1 mod square. And you end up in a scalar value. So this is a single value. The inner product of bra and ket is a single value, which is called, which will have more implications as we look at things. And then there is the outer product. So when you swap these two and do matrix multiplication, you end up with a larger matrix. So all of these have implications, which we'll see in a bit. Right, and this is sort of where quantum mechanics, quantum computing gets dangerous. So what I showed you earlier was a single qubit, and this is a single qubit. It has it's comprised of 2 bits of information. But when you decide you want to represent two qubits at the same time, what you do is you do something called a Chronicle product. And how the Chronicle product is done is this way. So you write down the first one, and then you write down, Chronicle product this, and then you sort of take it in. So 1 0 and 0 0, and then you sort of expand this guy. So this is 1 0, and this is also 1 0, and then you multiply these, and this is the sort of final form you end up with. So what's worth noting here is that when you had a single qubit, you only had to deal with two pieces of information to describe the quantum state. But when you have two qubits, you have four pieces of information which you need to describe the quantum state. And this doesn't stop. This keeps going on. So 2 raised to 2, 2 raised to 3. If you're sort of writing down 3 qubits at the same time, their actual representation would be 2 cube, 2 raised to 4, 2 raised to, and that's why quantum simulation is actually really difficult, because this gets out of hand really fast, and it doubles at every step. So say if you have 24 qubits, you're dealing with 2 raised to 24, which is an unimaginably huge number already. And then when you change to, so when your machine has 25 qubits and you want to simulate the same thing on a normal computer, you're not increasing 1 0, you're doubling it. So how many ever bits you needed to represent a qubit is there, you're doubling it. You need twice as much more for the very next qubit. And that means things get out of hand really, really fast. A very normal computer like ours has like how many GB? 16, 18 GB RAM. And 18 GBs is 18 into 10 raised to like 2 raised to a huge number of bits. If you had the same number of qubits, the very representation for it would have 2 raised to those many entries in its metrics. To represent it in a classical computer, you would need 2 raised to those many, and that's a scarily huge number. Like we wouldn't ever have enough memory to. So there's all sort of insane statistics which pop up, like, if you took every grain of sand on Earth and did it, you still wouldn't have enough to mark 2 raised to, I think like 2 raised to 100 and numbers like that. So what that means is there is no way. So unless you have this particular metrics, you can't represent what a quantum computer does. So all the operations you do will be applied to this to simulate the quantum computer. So if I want to apply any operation on this qubit, on a quantum computer, I just have to do a quantum operation and this will be done. But if I want to do the same thing on a classical computer, I'll similarly make another matrix of the operation and I'll multiply it with this, and the result is the quantum result. So if I have a 1,000 qubit quantum computer and it does, say, a set of operations, and I decide I want to simulate the same thing on a classical computer, that is going to be very, very difficult. And that's sort of the first, that's sort of where you start seeing how quantum computing gets really, big and out of hand for a normal computer. And then, so if these are states, how do you change states? So in our normal computer, the analog would be you have bits of memory, and then and then you apply operations on them, say AND gate, OR gate, and they change things. And these get complicated, and they reach your programming language, or whenever you click a button, all of those have been pre-programmed, and those bits get changed. But at the end of the day, it's gates acting on these qubits. And for our case, we also have gates. We are still working on the gate model. There is no sort of there is research happening on higher level abstractions, but as of right now, most of us still work with gates. And some of the most basic gate, this is the most basic gate, is the X gate. It is essentially the NOT gate in a normal computer. And so if you have a 0, if you apply the X gate on a 0, it'll turn into a 1, and vice versa. If you apply it on 1, it'll turn into a 0. So this is, so if states are represented as column vectors, gates are represented as matrices and unitary matrices. So conjugate of this when multiplied, this will still equal to 1. X transpose X will still be I. Again, not very important in our case. So the sort of important idea here is this is a qubit this is a gate which acts on only a single qubit. So a single qubit is a 2-dimensional vector. So the operation acting on it is a 2x2 unitary matrix. So this, so if you wanted to apply X on 0, what you would actually be doing in the background is you would be taking this matrix in a classical simulation, and you would be multiplying it with this vector, and then your result would be another vector, which is a result. And this is our good old outer product from earlier. And so this is we're just sort of expressing this in different ways. So if this is another way, this is the outer product way of expressing this gate. And so when you multiply x with 0, this is equivalent to just putting your 0 over here. And this, when you do the calculation, turns, this sort of turns into 1, and this turns into 0. So 0 into this thing goes away, and you are left with this particular 1, which is x1. So these are all different notations of doing the same thing. And yeah, so that's when you apply it on 0 or 1. And this is a sort of more contrived case. So if you're applying it on a superposition, what happens? So our earlier superposition was alpha 0 plus beta 1. So when you apply an X gate on that, you're applying it to both the basis states. So there's alpha into this and beta into this. And x of 0 is 1 and x of 1 is 0. So this sort of swaps. This beta comes over here and alpha comes over here, because 0s become 1 and 1s become 0. Yeah. So when you apply one X gate, when you apply one NOT gate classically, you're not just on a superposition. It's like you're applying the NOT on both the 0 and the 1. So you're, in a classical sense, you've done two computations here. And as the number of qubits increases, you're doing more and more and more computations parallelly. But this also comes with a lot of restraints about how you can get results and a lot of things like that. But we look at that over time too. Another gate, this is the H gate. Again, this notation looks a bit, a lot of math and a lot of stuff, but over time you get used to it and it becomes interesting. So the sort of, you're again starting off from the 0 state, but when you apply Headerman on it, this is H gate, which we call the Headerman gate. And so what it does is it takes it to a state which is not just comprised of 0, but 0 and 1, and then a 1 by root 2. We call the state the +1. So this is a superposition state. It's not just in 0 state anymore. It's not in 1 state anymore. It's in a superposition of both of these states. And if you apply Headerman to 1, now what you'll have is the same thing, but the phase has changed here. It's not positive sign anymore, it's negative. And these things matter a lot. So as you look on, as you go on to do more and more quantum computing, you'll see, especially I think there's a session coming up on phase kickback, where it's very important that this negative sign is sort of what drives many powerful algorithms together. The idea that you can cancel out many different things and only other things will be needed. All of that comes in from this sign. So even though it just seems like a plus or minus and it's a small difference, it makes a massive difference. In the long term, it changes things a lot. And then what happens if you're starting off with this state? Okay, you have this state, and what happens if you apply Headerman gate on that? And then if you do the math, you'll end up with 0. So this is another property which you see very often. So Headerman of 0 is plus, and if you apply a Headerman on that plus, you again come back to 0. Same applies with X gate also, right? X of 0 is 1, and if you apply an X of 1, it comes back to 0. And so these two are single qubit gates, and now there is a double qubit gate. So this is again a bit of scary looking notation, but if you sit down and take some time to read through it, it wouldn't be that bad. But here the important thing is, up to now we were all talking about operations which are applied on single qubits, but what if you wanted to apply an operation on 2 qubits? Okay, and this is also sort of where the quantum gets even more important. So if you think the Headerman gate is what superposition is, C0 is a sort of gateway into something called entanglement. And entanglement makes it worse for classical computers, because the more entangled the circuit is, we have theorems and proofs that it becomes even more and more difficult to simulate at all. So the more entanglement you introduce, it becomes all the more difficult to work it out in a classical computer. So the basic idea is, so this applies on 2 qubits. Okay, so I should have had a figure. My bad. But I'm sure one more figure will come up. And so if all the gates till now applied on a single qubit, this particular gate is applied on 2 different qubits. And how this works is, one of the qubits is designated as a control qubit, and the other one is designated as a target qubit. And if your control qubit is 0, it doesn't really matter. Nothing happens at all. And if your control qubit is a 1, whatever your target qubit is, it gets flipped. So an X gate is applied. And just like I wrote this out, and I wrote a 0 and then I applied the math and I worked through it. If you sort of do the same thing with a C0, you can apply the math and you can see that this formula boils down to this. If the control qubit is 0, no changes. If the control qubit is 1, FCR is applied to the target qubit. And now sort of the reason why I spoke of all this, and a lot of scary looking math on this. So just like you've seen that this is a qubit gate, I want you to take a sort of leap of faith and stay with me on the fact that this is also a qubit gate. Okay, so this is another sort of quantum gate, but this quantum gate has a property that it is controlled by the value 5. So you can decide what value of 5 you want to put in, and whatever value of 5 you put in, this function changes according to that, and that is the gate which is applied onto your system. You don't have to be stuck with just one parameter. As you can see, this is the U3 gate, which has 3 different parameters. This isn't quite as used anymore, but on the earlier IBM quantum systems, this was the sort of gate which is implemented in the hardware. So even though you will be writing circuits in a particular sort of way, I'm sure you've seen webinars where circuits were written and they were executed. What actually happens is the circuits we write are not the ones which are executed in the hardware, because the hardware is only capable of doing so much. There are only some gates which are actually hardware built into the hardware, and this was one of the gates which was very prominent in the earlier systems, the U3 gate. So this gate is special because according to the value of theta, phi, and lambda, as long as you manipulate these 3 values, any of the earlier gates we looked at, right? So Headerman, X, any single qubit gate, there are a lot of other gates, Y, Z, etc. As long as you manipulate these 3 values, you can reach anywhere on a single qubit. You can do any single qubit operation as long as you manipulate these 3 values. And this is the U2 and the U1. So they also correspond to other important milestones in the hardware. And but what I want you to notice is the fact that these are variables. We control these, and depending on whatever value we put in here, this gate changes. So whatever operation you do is completely dependent on which value of theta, phi, or lambda that you put in. So those are parameters. Okay, so now to sort of take a break from all the heavy math and talk about some history for a bit. Why variational quantum circuits, and more importantly, I'll be talking about one particular method in variational quantum circuits called the variational quantum classifier, and this is fairly easy to generalize into everything. There is a sort of there are some components which can be swapped into different things. So you can swap, say, one type of circuit with a different type of circuit, one type of optimizer with a different type of optimizer, or things like that. But the general idea behind all variational quantum algorithms is roughly the same. So we'll look at one in particular, and then I'll sort of leave the others to you, and I'll leave some resources which will let you look at more methods. And it'll also give you a very strong basis. At least it should give you a very strong basis for what variational quantum algorithms do in general. So the other methods will also be fairly easy once you get these ideas across. But why variational quantum algorithms, and why variational quantum algorithms is the question we need to see. So initially, so quantum computing sort of blew up after the Shor's algorithms idea. So the first concrete problem which can be solved only by a quantum computer was the Shor's algorithm. It could factorize very huge polynomials, very huge prime factors much faster than a normal computer could do. So interest in quantum computing blew up, and everyone started seeing what can they do with quantum computing. And so these are some of the first attempts at this thing. So some people decided to try applying quantum Fourier transform, which is a very integral part of Shor's algorithm, into applying into data sets. So if you've done some amount of signal processing, you know that we apply Fourier transform everywhere in there. We use it in a lot of places, wireless connection, wireless networking, so many places. So behind the scenes, Fourier transform is pretty much ubiquitous in engineering. It comes up in everywhere. So some people decided they'll apply Fourier transform in data sets, and they'll try to use the quantum parallelism. The fact that when you apply one gate and a qubit, you're doing more than one operation at the same time. And this is sort of the first first attempts at data processing using quantum computing. And then people started building quantum machine learning. So we thought, machine learning, since quantum computing may speed up a lot of things, maybe machine learning could be one of those things. And some of the significant works is the k-means method, which was presented in Europe's 2018, if I remember. And it had a provable efficiency, like it had a provable speed up over the k-means algorithm, which is a very popular machine learning algorithm. So q-means was much more faster than the q-means. Q-means was much more faster than k-means, and that introduced, how do you put it, that encouraged a lot more people. There was a lot of work happening. Almost every machine learning algorithm had its own quantum variances. The kitchen sink algorithm got the quantum kitchen sink, and so many methods. We have so even though we normally hear of only neural networks and maybe k-means and a couple of methods in machine learning, there are a lot of statistical techniques which go into machine learning, and good lot of them already have quantum mechanical analogs. And this is one of those moments which sort of like sped things up a fast, that there is a method which can do things. But both of these were purely theoretical, because as I'm sure everyone's mentioned, current quantum computers are not in a condition to, they're not quite the machines which are needed to do all the algorithms as we come up with. Current quantum computers have like a fault tolerance and a fidelity of like 99+%. But that means that when you do 100 operations, say like one might fail. And that's a terrible statistic. In the sense that when I hit an enter key on my button, I'm probably doing so many more operations than that. Our computers work in gigahertz speeds. That means the number of operations is like 10 raised to 8, 9 per second. Those many operations are being performed per second by our normal computers. And if there is a fidelity rate of 99%, that means 1 in every 100 is wrong, and that would be catastrophic. We would never get anything done. But we are still only in that stage at quantum computing. This sort of fidelity 99% issue is also a thing even in our current computers. Whenever we design ICs, there's all sorts of error checking mechanisms, fault tolerance checks, and all of that built into it. But modern computers have it down to a science, as in classical computers, so we don't really have to think about it, and we rarely even know about it. It's still an issue. However, it's much more of an issue for quantum computers, and that's how we come down to the famously called NISQ, noisy intermediate scale quantum computers. So that means is the algorithms, the computers we have at hand are noisy. They do make a lot of mistakes, but they still have the capability to do a lot of things, right? So like, we have this, what's the best we can do with it? And that's the sort of idea behind NISQ algorithms. And that means even though you can't do a lot of things, like there's a QAOA, which is a quantum approximate optimization algorithm for solving optimization problems, and a lot of things which you can't normally do with the current NISQ hardware. So what we did is we started to improvise. So we were like, okay, we have this only at hand, and making a full quantum computer could take a while. So what can we do with what we have at hand? And variational quantum algorithms are sort of the forerunners for NISQ algorithms. They whenever NISQ algorithms are mentioned, they almost always pop up. And this is because the idea here is a hybrid quantum classical algorithm. That means some parts are done in a quantum computer, some parts are done in a classical computer. So like I said, simulating a quantum computer is very difficult. So what we do is only those parts which can be done just by a quantum computer are left to the quantum computer. And there are so many things which our current computers do extremely well. And what we do is we offload all of those tasks, all the tasks which might be difficult for a quantum computer, all the tasks which a quantum computer still isn't capable of doing. We'll do it all on our classical computers, and only that one part which is extremely difficult for a classical computer, we'll send only that to the quantum computer. And that's the idea for a hybrid quantum classical algorithm, and especially variational quantum algorithms. Right. Okay, so this image will pop up a lot. To very go over things very fast. It's designed to run in shallow circuits, because the bigger your circuit is, the longer you design your circuit to be, the more likely that an error pops up. If you're running 100 operations, it's more likely that your one error has already happened. So make it short. If you do it in 50, it's likely that you'll get away with no errors. And the idea with variational quantum circuits is you run shallow circuit. So before the error comes into your circuit, you're done. And by design, they also deal with some of the errors, which again we'll talk about in a bit. So VQE is a variational method which is used to do chemical simulation. QAO is used to do approximation problems, and the particular one we'll be talking about, the variational quantum classifier, is done to do classification problems. So the initial state preparation and optimization done by classical processors, while the quantum circuit propagates the weights and produces output. We'll come back to this line. I feel like we'll have to talk about it a bit more before we can come back here. Right. Okay. So yeah, this is just the earlier image zoomed in. Yeah. So this is a sort of image of every variational quantum algorithm, and this is taken from one of my favorite papers in variational quantum algorithms. This is a survey paper which I would encourage anyone with any interest in variational quantum algorithms to read. It's very well written and it's very extensive. And this is a sort of roadmap for every quantum algorithm. And so how this works is, this is the quantum computer and it runs circuits and gives out the output. That's it. So we take out the output, we produce what's called a cost function, and we do the optimization with cost functions, and then we do updation of parameters with cost functions, and we put it back. And to make more sense of it, these steps, making a cost function and optimizing the cost function is basically what you think of as deep learning. I'm sure you've heard the word deep learning everywhere, AI and deep learning. These two steps are at the cornerstone of deep learning, and that means we are very, very, very good at it. Okay, we have like decades of algorithms, we have decades of methods, we have decades of techniques just dedicated to these. So all this, so we're really good at doing this, and we have a lot of methods for doing this, and we will do this with a classical computer. So that means we won't be getting any sort of paralyzing speed up or any of the promises of a quantum computer in these steps, which eventually we want to. So at some point we want to remove these steps also from a quantum classical computer. We want to do all of it on a quantum computer, but since we can't right now, what we'll do is we'll do all of these things which we can do really well on a classical computer already. We'll do this on a classical computer itself, and just running the circuits part. So I told you one of the reasons why running circuits is difficult, why simulating a circuit is difficult. It gets bigger exponentially per qubit. But there's also a lot of other caveats. So there are other methods of simulating which don't need such big matrices, but only if you have very small amount of entanglement. As the amount of entanglement, the sort of C0 sort of gets increases, it becomes more and more and more difficult to simulate circuits. So I guess that's the part which classical computers can't do at all. We'll just have a quantum computer run that, and then we'll do the rest of the parts ourselves in a classical computer. And that's the idea behind, that's the sort of core idea behind variational quantum algorithms. So we'll look at each of the steps. Like we'll look at each of these boxes, we'll talk about them. So the sort of first box is the input. And the algorithm we're going to be talking about is called the variational quantum classifier. And what it does is, it does a very simple task, a task which comes up everywhere in machine learning, which is classification. So the example which everyone in machine learning always brings up is, you bring photos, you take a photo, and you look at the photo and you want to see whether it's a cat or a dog, or you want to see, is this a cat or not? So you say, yes, no, it's a cat, it's not a cat. And you want to automate it. This is something we see every day. So there are face recognition systems, your own, maybe Google Photos or iPhotos, it recognizes you. So it's a classification problem. It's classifying that this is you, or this is not a cat. And variational quantum classifier also tries to do that. It tries to classify what is what. And so for that, the sort of prerequisites for that is that you need training set. So if you're doing it in a classical computer, before you decide to build a machine which tells whether it's a cat or not, you need a lot of photos of cats, and you need a lot of in general you need a lot of photos. And then what you do is you sort of give each photo to a neural network. In the deep learning approach, what you do is you give each photo to a neural network and you train it. You tell it, yes, this is, and then you have it predict. You run it through a lot of functions, and then it gives an output. It's like 1, yes, cat, or 2, no, cat. And then you know whether it's a cat or not. So if it gets it wrong, you sort of penalize it. You give it a sort of punishment, and in quote unquote punishment. So this is actually a set of mathematical functions. You optimize a set of mathematical functions. That's what actually happens. But yeah, so the idea is if it gets it wrong, you penalize it, and if you get it right, you sort of reward it in a very humanizing way of saying it. But what you actually do is you sort of control a set of weight functions, and till you get the output that you want. And so the first prerequisite for that is a training set. So you need a lot of photos of cats or dogs, of cats and other things. So and then the second thing is a cost function and an ansatz. We'll get into those. Let's first look at ansatz. So for that, we look into the quantum computer. So the first step is you need a quantum computer, and you can see some circuits running in here. And this might be a good moment to put in this circuit. Okay, so this U1, this really huge number is pi. Its drawers have some problems with pi at times. But this U1 should look familiar to you because we looked at it a while back. Yeah, this is the U1 gate, and this is a gate which is controlled by the value lambda. So as you change the value of lambda, this changes, and that means as you change the value of lambda, this can turn into a completely different gate. Like we were doing here, if you choose a particular value of theta, phi, and lambda, this will turn into the X gate, which we saw earlier. But if the values you give are changed, it'll turn into an X gate, which is just a completely different behavior. So that means as long as you control these three values, you can make the circuit do whatever you want it, which is you can train the circuit to do whatever you want. And that is the quantum part of things. So what that means is our core idea is to set up a circuit which is completely comprised of sort of gates like these. Okay, so all of these values is x0 you see here, x1, x2, x3, and so on. These are all values which we are going to learn. Okay, so our idea is that we'll learn those values. We'll given a lot of inputs, and then we'll get a lot of outputs, and we'll use the penalizing or rewarding mechanism that we said earlier, and we'll change these values. So those methods will change these values, not these values, and as they change this value, that means this circuit is completely changing. As a value of this x0 changes, this could become an X gate or a Y gate or a Z gate, and over time this turns into a circuit such that the purpose of the circuit is now to classify. So whenever you given an input, this circuit will now classify and give you whether it is a cat or not, and so on. So that is the training process, and that is our aim, to build a classifier, a machine which does that. So there is a couple more steps you need to do that for that though. So say you have decided you want to classify a cat's image. How the cat's image stored is it's stored in RGB values, which is red, green, and blue pixels. And you, the only thing when you look at a photo, what is actually stored is these RGB values. And what you have is a huge array of such values. So for every dot on your picture, there is an RGB value, and that is your input generally to a machine learning algorithm. But the problem is that's only for a classical computer. So that sort of data works only for a classical computer, right? This is for a quantum computer, it has to be in all data, or anything has to be in the form of that 0 or 1 state, 0, 0 state, 1, 1 state, or something along those lines. You can't have so it doesn't make sense to have like those are classical values. How are you going to bring them into a quantum computer? How are you going to put that value into a quantum computer? And then there are sort of two separate circuits which are important in this case. And the first case are the feature maps. So this is called the feature. This is one example of a feature map circuit, and these are some more examples of feature map circuits. This is probably one of the easiest examples to talk about. These gates are redundant, but anyway. So what you do is, say you decided that you're working on a data set with only 4 values. So you're given 4 values, which could be like age, height, weight, and one more data point, say gender or something like that. And the output should be is this person, say, obese? Like, is their BMI over a particular value? And so you decide you want to make a quantum computer do it. What you do is you first your first circuit would be something called a feature map circuit. And what the feature map circuit does is, your first data point, it will be sort of read into this as x0. Your second data point will become this x1, x2, and x3. So this essentially does is, now your classical information has become a part of this gate, and whatever state comes out after this gate is applied is representative of your classical information. So initially your state was 0, which is this, like this sort of a state, but the sort of, yeah, and then this gate comes in, and your data point is this particular value. So the next output will definitely have at least one column which is influenced by your data point, and so the next state is influenced by your data point. That means at this point, whatever is here is influenced by your data point. It is sort of representative of the data that you feed in. So this whole process is sort of analogous to you take in classical data and you have changed it into a quantum state. And there are so many different ways of doing this. And this is a poly feature map, which is one way of doing this. So here you would feed the values x0, x1, x2, x3 with your data points. And this is a different sort of poly feature map. And here the RX gates, and here there is also 2 qubit gates involved. And then here is another sort of feature map, wherein you would put in your values here, and this would come out in a different way. So why I have so many different ways is, we don't really know which one is good even now. Again, to sort of stress this point, anything I say throughout the entire lecture, like sort of 1 hour, could be completely wrong tomorrow. This whole field is moving at a really, really fast pace. There are papers coming out each day which completely disprove everything which we knew up to yesterday. And these are some methods that we know right now. We don't know which of these is the best. We don't know which of these gives the best outcome. We don't know which of these gives the best output. Those are all open questions which we all have to tackle. And yeah, so I'm sort of presenting a lot of options to you. So whenever you have a quantum circuit, these will this is the way in which you bring your classical data into a quantum circuit, and these come in here. So the first set is you take in your training set, you pass it through this circuit, so you finally finally get a state which is representative of your training set, and then the next step is to and so this is the next step. So so this whole thing I told you till now is an embedding map. So what it does is it takes your classical data and it embeds it into a quantum state. So it's called an embedding map. And so after that, our aim was not to move classical data into quantum data, but to build a classifier. So we want to build a circuit which will tell us whether is this person overweight, or is this person, or to take the more famous example, there's a data set in machine learning called Iris data set, which is sort of considered a first test bench for anything. And what it consists of it's got the sepal width, sepal height, petal width, and petal height, I believe, of flowers. And then you read their data, and then you look at this data and you decide, is this a particular species of flower or not? And that's what we'll be doing here as well. So that's probably a better example. Anyway, so our idea here is, so we'll feed those 4 data points into this, and we'll get a state which is representative of the petal width, petal height, sepal width, sepal height. And then we want to build a circuit our state which we already prepared is around here. And then when it passes through this circuit, what has to happen is that when we measure values here, it should tell us if it's all 1, say, it means that this is a particular species of flower. And if it's all 0, it should say it's not that particular species of flowers. And these are some of the circuits. This is a small part of the circuits which are there are so many different circuits which have been used, which are used for variational quantum circuits. And these are all learnable parameters in here. So our aim is to learn these parameters. So the x0, x1 here, our aim is to learn these parameters so that our circuit will do what we want us to do. We'll classify. This is one sort of circuit, this is another. These are all different types of circuits. But what's important here is even some of the easier circuits in this. So as long as you start introducing, this is the CNOT gate from earlier, by the way. This is the control and the target qubit. As long as you start introducing enough CNOT gates and entanglement, what happens is even the easiest of these circuits becomes intractable to run. So it becomes very difficult to run even the easiest of these circuits on a classical computer. So I'm not talking at this scale, because here we have only 3 qubits. That means like 8 values in a matrix. And even if you have like a lot of entanglement, you can still get through this. But say if you had like 50 qubits, you'll get out of hand really fast. And so what that means is our classical computers cannot. Our classical computers will very fast become unable to represent these. That means we have to do this in a quantum computer, and this is the part which we absolutely must do in a quantum computer, because we can't do it in a classical computer, and that is the only part which will actually run in a quantum computer. All the other parts will be offloading onto a normal computer, and the reason for that is the fact that our current computers are sort of unreliable. They're NISQI. Okay, and how do we do this? Another slide. Again, let's not be intimidated by huge selection. These have meanings which make sense over time. So how do we do this? And if you are at all familiar with machine learning and AI, by now you should have seen a pattern. We have a couple of values that we want to learn. We have a way of inputting it. And that means the next step is create what's called a cost function. So this is another way of representing the cost function. So this U and U dagger should have been swapped. But this U theta stands for our particular trainable circuit. This raw stands for our input circuit, and there is an observable circuit which so you're finally doing a measurement, right? At the end of this, there'll be a measurement gate which is considered as the observable. Otherwise, you can add some more gates and then measure, which changes the observable further. And the trace is because this is from a different sort of notation called the density matrices, but they're not very important. So the sort of more important thing in hand is what is a cost function? The idea of a cost function is a lot more important. So what you do is you've taken your data point, the first 4 values, you pass them through the circuit, you pass them through the variational circuit, and you gotten a cost function for that, and you got an output for that. And then you sort of compare it. So I know whether it is a particular species of flower or whether it's not a particular species of flower. So when the circuit tells me it's all 1, I know it's not that flower, it's 0. So what I do is I create a cost function. That's a function which so the sort of whole idea is that so the idea of the cost function is if I get it wrong, the cost function increases, and if I get it right, the cost function decreases. And what I want to do is I want to decrease the cost function as much as possible. So if this circuit does wrong, the cost function increases. And if the parameters I learned and the circuit does right, it decreases the cost function. And I want to decrease the cost function as much as possible. That's sort of my game plan. And this is a very large notational way of saying I'll take the value from here. I'll take its output, and I'll compare it to what should be the real output. And I'll create a cost function. And there are so many different ways of defining cost functions, especially which come in from machine learning. We have like binomial laws, we have logistic laws. Yes, we have all different. Like that's an entire field of study by itself. But a very simple one would probably be like if it is correct 1, and if it's wrong 0, or some other value. But so that's essentially what this big notation comes down to. Okay, so that gives me a cost function. And now the game plan is. I've run through this and I've created a cost function at one point. So how this sort of map comes about is I create a value, and then I try with a different sort of parameter. Then I try with a different sort of parameter. I try with a different sort of parameter. So at the point where the circuit does what I want it to do, the cost will be very low, right? So the cost will be at this sort of bottom here, and I want to reach this bottom. If I try every set of parameters, this is a sort of map which I will create. And I want to reach this point in the map. So I want this set of parameters, which gives me this bottom of the map. And that's the idea behind a cost function. And how do we do this? How do we take the output and look at the cost function, and we decide how to change the parameters? And that's the optimizer. Again, this is a whole different field of study in machine learning. This is all sort of not just in machine learning. Optimization algorithms are like a field of their own. and they have there's a lot of work happening in that area. And you might have heard of things like gradient descent or gradient descent or all of its cousins, RMS prop, Adam, and so on and so forth. Or so all of these use something called the gradient, which is a way of finding partial derivatives and then using partial derivatives to change the values. But there are also methods which very often we use in quantum computers, especially a lot of which are pre-built into Qiskit, like the Kobila, which is called the constrained optimization by linear approximation, and a lot of other methods. So again, this is a whole field of algorithms, and this is another whole field of algorithms which we are really good at. Okay, so there is a lot of cost functions already pre-built into Qiskit. There is a lot of optimization functions already pre-built into Qiskit, and Qiskit also has the capability to sort of connect with other software which we have written purely for the sake of writing cost functions and optimizations. So we have all sorts of software built purely for that. We have TensorFlow, we have PyTorch, we have JAX, we have like all sorts of things which do these very, very efficiently. Like they went down to a science as well. And so these two parts are then sort of handed over to a normal computer. And after this optimization is over, it gives you a new set of parameters, which are then, like you go back and then you plug those parameters into here. You don't change this because here is you don't manipulate any of these. This is just for input, but then you manipulate these values. So it's sort of like this. Let's say these circuits are together. This first circuit is just for reading the values, and then it gives on to our circuit, which we change all the parameters, and then we get an output. So this goes on in a loop. Okay, so the first time you don't get it right, the second time you don't get it right. Often it goes on in machine learning. It can go on to like millions of epochs. One loop is called an epoch, and so it can go on to like millions of epochs. And after you have run it through a lot of epochs, if your cost function is good and your optimization algorithm is good and your circuit is good, that's a lot of conditions to put in there. You finally end up with a classifier which does what it wants, which does what it wants, which does what you want it to do. Okay, and this seems like a lot of ifs, and it seems like a lot of like if this works and if this works and if this works. The thing is, especially the bottom half, you don't really have to worry a lot about. We have a lot of expertise in this. We've been doing a lot of research in this. We know what works with what and stuff. But obviously, because it's quantum, this has changed a lot too. We are coming up with new ways of writing cost functions. We're coming up with new optimizers called quantum. So there's a quantum natural gradient optimizer. There are new cost functions which work better for quantum circuits and all that. And as for circuits, I've already shown you like 6 circuits in just 2 pages, and there are a lot more of circuits. So optimization can be done by parameter shift gradient descent. This is just, I mentioned gradient descent. This is just one of the methods of doing gradient descent. Here the idea is that if your value is theta, so if I decided that I was going to use the value, say 0.3 here, I also run one more circuit with 0.3 plus 0.0001, and I run one more circuit with 0.3 plus minus 0.0001. And that would be this and this. The plus and the minus stands for a minor increment, a tiny increment to the negative side and the positive side. And then I subtract them, and then I go through one more constant, and I'll still find the gradient. So those of you who are familiar with gradient descent, this is one of the methods of finding partial gradient descent. But for others, you don't really need to like be too worried about it. Gradient, there's a lot of resources around gradient descent also, and it's fairly easy to pick up. But I think the sort of more important idea here is this sort of flow. The idea that your training data will be classical. You'll pass it through a quantum circuit. You will just do the most necessary operations on a quantum circuit, the ones which are difficult to do in a classical computer. You'll take the output. You'll pass it through a lot more classical processors. You'll build a cost function. You'll build an optimizer, and then you'll go back and update these parameters over and over till you have a circuit which does what you want it to do, and that's sort of the output. So the output is like these are different ways of taking output, right? In our particular case, we are variational quantum classifier is pretty much dependent on the bit string. That means that's the output. So if I So if it is a flower, I want it to be 0000, or if it is not a flower, I want it to be 1111. And that's not the only way of doing bit strings. There is a lot of choices here. One another sort of popular choice is parity. So if it's an odd number of zeros, it is a flower, and if it's an even number of zeros, it's not a flower. And that's for variational quantum classifiers. And there's a lot of other ways you use this. So in the method I mentioned earlier called VQA for chemical simulation, your idea is not to classify and find out what is good, but to train the circuit so that you can find the lowest energy of a molecule or something. At that point, you're not very interested in what the exact bit string which comes out is. What you want is a circuit which will find you the lowest quantum state possible. And then there are other applications like QGANs, where your idea is to create a machine which creates data. So in here we have data, but what if you want to make a machine whose job is to create the data? So in that sort of situation, you're more interested in probability distributions and gate sequences, quantum operators. So the thing is, I've just explained one facet of variational quantum algorithms, the variational quantum classifier, and I focused mainly on what are the parts and why they are here. But as you can see, you can swap all of these. If you decide you want to make a circuit for a different reason, you swap the parts. You decide this is not the sort of circuit I want, and I don't want to measure the bit string any longer. I want to find out what the quantum state is, and so on and so forth. As you change these parts, you reach different applications of things. But the thing again I want to focus on is this overall flow of things, and this is how a variational quantum algorithm in essence works. Okay, and so some resources that I've put in here, I will put in some more before I send out these slides. Is this brilliant blog post in variational quantum algorithms by Michael Stretchley. Qiskit textbook. So I mentioned earlier that we have software which are really good at doing all this, and Qiskit has the ability to interface with these already built in. So the second link is a beautiful resource to how that can be done with Qiskit. The final one is a Qiskit machine learning tutorial. So Qiskit has an entire library called Qiskit Machine Learning, which is solely focused on machine learning for quantum computers. And this is the sort of documentation tutorial page. It's written in a very simple language, and it's very understandable. So if you want to see more concrete examples in terms of code, if the way you understand things is better in code, that's a really cool place to go. But I would recommend first you go with this, have a good read, because they go into a lot more detail than what I've covered, and they provide a lot more links as well. And then you come back to the Qiskit, you read the Qiskit textbook to have a better understanding of concepts, and then finally look at code here. And yeah, that's about all I have in hand now. So again, let me emphasize, if this seems a bit overwhelming, that makes sense. Feel free to ask as many questions as you want, and I'll try to answer as much as I can. But the overall idea is to be familiar with things. And if you've gained any concept out of this, that's already pretty good. Because when you come across this again, when you sit down and decide you want to learn this, you want to look at variational quantum algorithms and you read it again, this will come back to you. And this will have a sense of familiarity and it'll help you a lot in there. That's the sort of overall aim of this whole thing. And yes, so if you have any questions at all, I think you take them. I think we're over time by a bit. Oh, okay, we're over time by 10 minutes.
It's okay.
Yeah. Okay. Yeah.
Hello.
Yeah, please. Sir,
that TR function is the trace of matrix?
Yeah, it's a trace of the density matrix. I just didn't want to go into the density matrices because I wrote the rest of the notations in terms of I didn't define states in terms of matrices, right? Define them as vectors. So I didn't want to go into density matrices as well. It's just a standard form of writing a cost function. So I just put it up there. But yeah, it is the trace function.
Okay. So since I am a mathematics PhD scholar, so I would love to go into that density matrix
There is a
Yes,
lot
sir.
of work happening in tensor algorithms, especially in this field. If you're interested, that's a beautiful field to work.
Okay. Okay, so and sir, you explained from very beginning, and everything was so clear. I really appreciate your talk. This was great. Thank you so much, sir.
Thank you.
Thanks for your detailed presentation, sir. It was exceedingly informative. And I guess we have arrived at the end of our session. And I extend my gratitude to Mr. Vishnu Ajith for joining hands with us. And thank Dr. Manjula Gandhi and Dr. Gayatri Devi for leading and supporting us throughout the process. I thank each and every one of you for joining the session. Stay tuned in the Discord server for announcements and updates. Recorded video of this session will be posted to the same. As always, feel free to post your doubts and queries in Discord. The team is always ready and pleased to help you. Timings and links for further sessions have been circulated through Discord channel. Meet you all in the next session by Mr. Jayesh Parashar at 2 p.m. I thank you all on behalf of Team CIT Quantum Hackathon 2022.